Hi, everybody. I'm Claudio Lungu. I'm the director of the Deep South Center for Occupational Health and Safety at UAB, and it's my pleasure to be the moderator of the last pilot project research session. This session is going to be a little bit different, considering that everybody who is presenting today were recipient of the pilot project in the Deep South Center. I wanted a little bit more from our pilot project recipients, so I wanted you guys to present and work a little bit more. So each presentation is going to be 10 minutes, followed by 5 minutes of questions. I want to thank you, everybody, for being here and for your hard work in working on these pilot projects. And with that, I'm going to start with actually introducing our first presenter. Our first presenter is Hengxiao Huang. He is a postdoctoral associate at Alabama State University, and he is going to present fabrication and evaluation of sustainable fibers for volatile organic compounds. So Huang, it's your.
Thank you, Dr. Lungu. Okay. So, hello everyone. I'm going to present my work, and the purpose of this work is to test the effect of carbon nanodiamonds on the adsorption of volatile organic compounds. And in this process, I have made two types of scaffolds. The first one is it is a 3D printed scaffold, and it has micro scale pores and structures. And the second one is the electron spawn scaffold. It has a nanoscale pores. So first, I want to talk how I printed the cellulose acetate scaffold, and I was using this EnvisionTEC 3D bioplotter to do the test and to do the study. And on the slide 3, excuse me, I cannot locate which slide I'm looking to. So now I should look at slide 3 now. On the slide 3, I'm using 25% of cellulose acetate in the DMAC and acetone solution. Oh, sorry, I'm using 30% of cellulose acetate in acetone solution and using the listed printing speed, pressure, and needle diameter and offset to do the printing. Then I immersed the scaffold with 2% of carbon nanodiamond water solution. And it finally evaporates the water solution in the oven. Then I made another electron spawn sample using 25% of cellulose acetate in DMAC and acetone solution, and the needle to collect the distance and the flow rate and the voltage adjusted like this. To do the adsorption test, I placed all the samples. Also, the electron spawn film was also immersed with the same volume of carbon nanodiamond solution. All the samples was finally put into a vacuum oven with a dichloromethane environment, and the weight difference between and after 2 days was measured, so that it can test how much dichloromethane can be absorbed. And on the on the page 4, slide 4 on my PowerPoint, I'm showing you the cellulose acetate micro scaffolds I printed, and it has a very small pore size at 99 micrometers average pore size. So it's a micro scale pore size. And on the page 5, I'm showing you the electron spawn film making of cellulose acetate. Now the key information result is on page 6. I measured the adsorption of dichloromethane. This is a volatile organic compound before and after 2 days. That's the weight differences. So I'm here on figure 6. I'm showing you the difference from figure 6 on slides on page 6. We can see that by including 2% of carbon nanodiamonds, both the electron spawn film sample and the 3D printed sample has had a higher adsorption of volatile organic compounds, the dichloromethane. So here on page 6, the figure 6, the blue bar is the 3D printed scaffolds with nanodiamond. The orange bar is the 3D printed scaffolds.
I think you should go. Okay, now we see it, but before you were on the wrong slide, so you can. Now we see the slides.
I'm sorry. I'm sorry. Yeah, now I see it. Yeah, great. Yeah, I was looking at my PowerPoint. Yes. So you can see here. This blue one is the 3D printed scaffolds with nanodiamonds, and the orange one was the 3D printed scaffold without it. And the gray one is the electron spawn film sample filled with micro scale pores and nanodiamond added. And then the bright yellow one is the electron spawn film sample without nanodiamond. And we can see that by adding carbon nanodiamond, the adsorption has been increased. But this is the average weight change by percent. That's the unit. So we can see nanodiamond contributed to an increase of adsorption. And another difference is that we can see that without the nanodiamond, the electron spawn micro scale sample has a higher adsorption than the electron spawn. The 3D printed sample has a higher adsorption than the electron spawn sample. And we assume the reason is that by 3D printing, the sample has thickness, so it's three-dimensional, so it should have a larger volume and surface area for adsorption. Lastly, when nanodiamond is included, the change in the adsorption property is larger in the electron spawn sample. That's what we observed. So that's the result. And I want to, I want to change to the page 4. Yeah, let me change it. So, here it is. Thank you. So I want to admit one thing. Initially, in our proposal, we said we want to do a very sophisticated adsorption test with formaldehyde. And however, due to the COVID-19 issues at that time, we were not able to conduct the collaboration test. So the experiment, the complexity and the technical level of the experiment is reduced a lot. So I have to admit this thing. So but then we did some other work. However, it's not focusing on the topic we're proposing. We tried to print these 3D scaffolds for the teacher engineering purposes. And our unique contribution here is that we printed the scaffolds with pore size smaller than 100 micrometers. But as we know, in the extrusion-based printing, the resolution is relatively poor, and the average pore size sometimes is 500 micrometers or 1,000. 1 millimeter or larger, and that's not suitable for tissue engineering. While in most cases, the suitable range is like 100 to 250 micrometers. The pore size for tissue engineering. So we achieve a smaller size than most of the reported work. And how we achieve that is we find optimize the combination of printing speed and the pressure of the compressed gas, and also the needle dimensions, and also the ink compositions. By this way, we can achieve that. And so this marks the first work that printed 3D porous scaffold that specifically with the cellulose acetate, and also the smallest pore size with extrusion-based printing. And it has been published in the Journal Additive Manufacturing in December 2019. So though it's a little different from the focus of this proposed work, but it's still some achievements. So that's all of my presentation. Welcome to have your critiques and questions.
I think that's very interesting work. And there are a few questions, I guess. Let me see. First, could you I think that it wasn't very clear. You had two types of structures, right? One was the electrospun structures and the 3D printed structures, right?
Yes.
But they were both based on the same chemicals, right?
Yes, both cellulose acetate.
Cellulose acetate, right? So, and you also showed that the 3D printed ones showed a very uniform structure, which is expected, obviously, compared to the electrospun one, right?
Yes.
So, did you have a chance? I didn't understand that very well. To check any of the absorption on the 3D printing structure? Absorption properties of the VOCs, of the volatile organic compounds, or not?
Yes, we did a test on both. Okay. Yeah.
And what was the role of the? Let me see. Yes, you had the nanodiamonds, which you had implemented on. I mean, added to both structures, the electrospun and the 3D printed. So what was the initial thought about that? What did you hope to achieve with that?
Yes. So what we hope to achieve is improved absorption capability from the carbon nanodiamond. Initially, the original chemical cellulose acetate, it has some absorption properties. And as a result, cellulose acetate has been used for some filtration or absorption applications like the filter in the cigarettes. But since this is a bulk material, and so we want to further increase its absorption properties, and then we think about carbon nanodiamonds. The carbon nanodiamond, first is it has lots of nanoscale porosities in its powder morphology. So the surface area is very large, and due to this nanoscale porosities, it can absorb more VOCs. So we want to utilize this potential to increase the overall absorption properties. So we put this onto the cellulose acetate substrate.
Because my impression is that, with the nanodiamonds, you basically increase the filtration properties rather than absorption properties. So filtration and absorption are two different things here. You filter basically particles at very small dimensions, even nanoparticles, and you filter molecules of organic vapors. So I think with the nanodiamond, you increase the filtration capability rather than absorption capability. Maybe I'm wrong, but that's what I see.
Dr. Longo, I think you are correct. We didn't test the filtration properties. So theoretically, it should be the filtration. We just probably accidentally see that it has some absorption properties, but it is not strongly supported by enough evidence. So okay. I believe you are right.
Okay. Any other questions? Okay, thank you. I'm going to introduce our next speaker, Isashikin Hoditawaku Arakinje, and she is a MD and an MS. She's a graduate student she's a graduate teaching assistant at Mississippi State University, right? And she's going to talk about the impact of prolonged exposure to slippery surface on static posture stability. I think you are still a graduate assistant, or you completed your studies?
Yes, I am. Yeah, okay. I'm a GTA.
Okay.
I'm completing my PhD.
All right. So hopefully that helped, that funding helped you with your studies, and I'm looking looking forward to see your presentation. Okay.
Thank you. Can I start?
Sure, go ahead.
My line of research is fall prevention at workplace. So if we look at the statistics of falls at the workplace, we'll see those numbers are very high. A lot of people die and a lot of people get injured with the falls at workplace. And these falls are going to impact the worker, like death, permanent disability, injuries, loss of income, and also the workplace, because they are going to lose a worker, maybe permanent, maybe temporary. So maybe temporary. So they are going to have less productivity. Also, the workplace has to pay for the medical bills, compensations, replacement workers. So it's going to add to the economic burden of the workplace. Therefore, if we can prevent these falls, we can save a lot of money, time, and energy. To prevent these falls, I don't know, slides are slipping. To prevent these falls, we have to identify the causative factors of these falls. What's wrong with this? I'm sorry. Can someone go to the next slide? Thank you. We have to identify the causative factors of the falls. One of the major reasons for these falls is slips and trips induce loss of balance. Loss of balance can occur due to many reasons. I have chosen two factors in my study. One is the fatigue, and the second factor is the nature of the standing surface, which is dry and slippery surfaces specifically. On the next slide, if you look at the previous studies that were done on slippery surface, there were few studies done on short-term exposure to slippery surface, and there were some studies that were done on long-term exposure to dry surface. But so far, no one has looked at what happens to people's balance when they were exposed to prolonged exposure to slippery surface. This is very important because if we think about some workers like kitchen staff, military, firefighters, they have to walk on slippery surfaces for hours. So this is a much needed research area. That's why I came up with this idea. On the next slide, you all can see my methodology. I had 18 participants. They were all young, healthy males. I cannot, okay. Can someone control the slides for me? I'm sorry. Thank you. They were exposed to a dry surface and they were asked to walk for 1 hour on one day. And also they were supposed to walk on a slippery surface for another 1 hour on a different day. In addition to walking, they were carrying this box, which was 10% of their body weight. And the slippery surface was prepared with a glycerol solution, a vegetable-based oil. And if you can see on the slide, they were supposed to wear these slip-resistant shoes to minimize slipping. And also they were attached to this fall arrest harness. So if they slipped, they are not going to sustain a fall, but the harness is going to catch them. Their balance was tested on the dry surface and on the slippery surface before they start walking, at the middle of their walking, and at the end of their walking. That means 0 minutes, 30 minutes, and 60 minutes. To measure their balance, I use this instrument called force plate. If we can go to the next slide, this force plate gives us some variables, we call them sway parameters. That means it tells us how much our participants sway. That means, as we all know, when we lose our balance, we are going to move in different directions like this. We call that sway. The postural sway variables can be measured by the force plate. Since this indicates the sway, we need these numbers to be lower as possible, because if we are swaying a lot, that means our balance is poor. If we are swaying less, that means our balance is good. So this graph shows you how much my participants swayed in the anterior-posterior direction or in this direction. And you can see the black bar represents the dry surface and gray bars represent slippery surface. And they were plotted for 0 minutes, 30 minutes, and 60 minutes. You can see the values are lower for 0 minutes compared to 30 and 60 minutes. That means my participants had better balance at 0 minutes compared to 30 and 60. The differences were significant between 0 and 30 minutes. On the next slide, we can see how much our participants swayed in the medial lateral direction, this direction. Once again, we can see they have swayed less when they were at 0 minutes compared to 30 and 60 minutes. That means participants had better balance at 0 minutes. On the next slide, there's another postural sway variable which gives us an overall idea of their swaying. Once again, they had less values for 0 minutes. So these all were time main effects. That means what happens over time. What about the surface? On the next slide, we can see, to remind you, black bars represent dry surface, gray bar represent slippery surface, and you can see all the time participants had more swaying when they were exposed to the slippery surface. The numbers are higher. That means their balance was poor when they were exposed to the slippery surface. On the next slide, I'm showing there's an interaction of the results. The interaction basically expressed that the participants had better balance on slippery surface and at 60 minutes, which contradicted my hypothesis, but it was the only sway parameter that contradicted my hypothesis. But I have an explanation for that, which I'm going to explain in the discussion. So on the next slide, as I have discussed so far, my participants had better balance on dry surface compared to the slippery surface. The reason for that, when we are walking on a slippery surface, we have less friction between our shoe sole and the walking surface. We are experiencing it these days with this ice and everything. When we experience that, we experience slipping. The ones we can experience, we call them macro slips. But there are some smaller ones we cannot experience, we don't feel it. We call them mini and macro slips. So every time when there's a slip, whether it's a mini, macro, or micro, our balance control system has to recorrect our position. It has to work repeatedly to maintain our balance. That's why we are going to have poor balance on a slippery surface compared to the dry surface. On the next slide, as I have been discussing, the participants had better balance at 0 minutes compared to 30 and 60 minutes. That means over time, their balance is going to get decreased. The reason for that, when we walk for long hours, we are going to get tired. So as our balance control system. So our balance control system is getting tired over time. That's why our postural control or the balance is getting less over time. We call that fatigue or overexertion or tiredness in lay terms. The interaction I told you about, the having better balance on slippery surface at 60 minutes, we can explain that with a concept called anticipatory postural adjustments using co-contraction. What that means is, when we are anticipating something, when we know the floor is going to be slippery, we brace ourselves, we get ready for that situation. So my participants knew the slippery surface that was slippery, so I had to be ready. We do this with co-contraction, means contracting front and back muscles of the leg at the same time. So then we are braced. So that's how I explained that result. If I had EMG data, electromyography data, I could show that with objectively. I had EMG data, but unfortunately our lab computer crashed after my 14th participant, so I lost all the EMG data. Apart from this data I collected motion capture data to assess their gait parameters, and lower extremity joint angle changes, but I'm still processing those data. On the next slide, I have my conclusions. As I told, over time, our balance is going to get decreased. It doesn't matter the surface, whether it's dry or slippery, our balance is going to get decreased over time. But that balance decrements are more pronounced when we are exposed to a slippery surface. So what's the importance of this study to the industry? We know when people work for long hours, they are going to get tired. We cannot prevent that. But if we can provide them frequent rest intervals, they can work, regain their balance during the rest, and start fresh for the next working session. By doing that, they will have less balance decrements, so they will have less falls at the workplace. So on the next slide, thank you very much for listening. I would like to thank NIOSH for their support with this project, my co-advisors, Dr. Haris Chanda and Dr. Adam Knight, and especially my participants, because they had to walk for 1 hour and another 1 hour on a slippery surface carrying a box attached to the harness. It was a little bit challenging, but they were wonderful and very understanding. If you have any questions, I would be happy to take them. So I think we are muted.
Here is a question.
Yes.
Who were your participants and how did you recruit them?
So my participants were young, healthy males, collegiate males. So they were supposed to mimic new workers, because when somebody go to work, like when they recruit a construction worker, they will be new workers. So my participants were supposed to mimic new workers without an experience. So I recruited them with ACSM guidelines, recreationally active. That means at least 3 days a week, 150 minutes of aerobic exercises and at least 120 minutes of strength conditioning. So that according to that ACSM guidelines.
Yeah, that's but it's also the fact that the young and very fit people, right?
Yes.
How this would translate or reflect to people who are maybe not that fit, and probably they are going to have more accidents because of the fact that their body cannot really adapt so fast to the condition. So I know that this is for employees who are starting their job, but it's possible that sometimes the employees will start at later age. They change jobs. They work in, I don't know, some other industries, and they move packages in a warehouse. So yeah, how that did you think about continuing or looking into this aging population, which could be differently affected by the slippery surfaces?
That's very true. My oldest participant was 35 years old. Still, they don't represent most of the working population. That's true. In my manuscript I prepared, I suggested future work with older populations, pathological populations, or obese populations, because when they are obese, everything is going to get changed. So those are some future work we could continue on.
I don't see any question, but my comment was, this is very important indeed for obese people, because almost 40% of the population in the US is overweight or obese. So it's definitely the way they would be affected by exposure to slippery surfaces is going to be different. But I think it's very interesting work, and congratulations for your manuscript. Thank you.
Thank you very much.
Okay, so let's see. I think we are doing very well time-wise. We are just on the minute, I would say. So our next speaker is going to be Anne Mulholland. She's a doctoral student at the University of Alabama. She's also in kinesiology, which is she's a PhD student in the Department of Kinesiology. It's always hard for me to pronounce. She's going to talk about the effect of work-to-rest cycles on cardiovascular drift and maximum oxygen uptake during heat stress. I think that's a very interesting topic, and I am actually interested very much in heat stress, probably from a different perspective, but I'm looking forward to listen to your presentation. Go ahead, Anne. Thank you.
Thank you so much for that introduction. Hopefully you find this presentation interesting. So I used this as a project as well. So we're going to be talking about the effect of work-to-rest cycles on cardiovascular drift and maximal oxygen uptake during heat stress. What does that mean? Hopefully by the end of this presentation, you know. So a couple terms to define before we get started. One of the things that we measured in this study was work capacity, which is just the total amount of work that someone is physically capable of performing. And we measured work capacity as maximal oxygen uptake, or VO2 max, which is just how much oxygen someone can use when they're working as hard as they possibly can. In this study, we used treadmill running. We also measured heart rate, which is the number of times that the heart contracts per minute. And then we also measured stroke volume, which is how much blood is pushed out of the heart each time it contracts. So the background for this study, there are a couple key concepts. NIOSH has this publication which provides recommendations for occupational work in the heat and how to mitigate the effects of heat exposure. And two of the things that they recommend are the use of work to rest ratios. And they also recommend that work intensity does not exceed 40% of someone's work capacity, or 40% of their VO2 max. The other thing that we know is that heat stress diminishes work capacity. And one way that that happens is through this phenomenon called cardiovascular drift, which is what this figure is showing here. So cardiovascular drift typically is measured during steady state continuous exercise, so a little bit different, there's no rest breaks. And we see this increase in heart rate and a decrease in stroke volume over time. And this cardiovascular drift is associated with a decrease in VO2 max, or work capacity. And if you look at this figure here, you can see that the black bars compared to the open bars show us that this phenomenon of cardiovascular drift and the associated decrements in VO2 max is exacerbated during exercise in the heat compared to comfortable conditions. And so the purpose of this study was to determine whether cardiovascular drift and the associated decreases in VO2 max occur over multiple work to rest cycles during a simulated moderate intensity work bout in hot conditions, in accordance with all of those NIOSH recommendations that I previously mentioned. And so we hypothesized that cardiovascular drift would accumulate over multiple work to rest cycles, and we would also see a proportional decrease in VO2 max, similar to what this figure is showing here. And so in order to test these hypotheses, we brought 8 subjects into the lab. We followed all of the assumptions from the NIOSH guidelines. So our participants were under age 40. They were hydrated, which their USG was less than 1.02. They were physically fit. They had a VO2 max, an average VO2 max above 40. They were free of disease, and they also exercised wearing pants and long sleeves, as you can see in this picture here. Moderate intensity work was 230 watts, which, to translate that, is just a casual stroll on the treadmill. And they exercised in the heat in these hot conditions, approximated an average summer day outside in Alabama. So it was about 93 degrees Fahrenheit and quite humid. We were a little bit limited in the humidity with our laboratory equipment, and we needed to keep our computers working. So it's actually more humid outside in Alabama, but 55% got the job done. So the first visit was a control visit. We measured VO2 max, had a familiarization protocol, and then the following 2 experimental visits were counterbalanced. The first visit, or one of the visits, 120-minute protocol, consisted of 45 minutes of work in the red, followed by 15 minutes of work, or 15 minutes of rest, in the black, repeated once, and then followed by measurement of VO2 max at the end. We measured heart rate and stroke volume near the beginning and at the end of each work bout so that we could assess cardiovascular drift over time. And then on a separate day, participants replicated the first 15 minutes of that 120-minute protocol so that we could measure VO2 max at 15 minutes before cardiovascular drift occurs. And the purpose of the separate visit was so that we could measure VO2 max. You can't measure VO2 max twice in the same visit. It's not methodologically sound, and nobody wants to do max tests twice in one day. Participants wouldn't agree to that. And so what we found was that despite rest breaks, core body temperature increased about 0.5 degrees Celsius or 1 degree Fahrenheit over just 2 hours. So the rest breaks were not sufficient to return core body temperature to baseline, and it continued to increase throughout the protocol. We also saw accumulated cardiovascular drift. And so these bars represent percent change from that initial 15-minute measurement that we took. And heart rate represented in the red, you can see was elevated about 10% at the end of the first work bout. It remained elevated at the beginning of the second work bout. So after they rested, heart rate remained elevated from our initial measurement. And then at the end of the second work bout, heart rate increased further for a total change of 18 beats per minute in heart rate. And then you can see stroke volume in the black bars showed a similar pattern of decrease over the same period of time. However, despite this accumulated cardiovascular drift, you can see VO2 max represented by the open bar was not significantly different after the second rest break. Those dots represent the individual responses to VO2 max between 15 and 120 minutes. And this variability is about what would be expected with repeated VO2 max testing on separate days. So why was VO2 max unaffected despite that cardiovascular drift? And to answer that question, it would be helpful to know how heart rate, stroke volume, and VO2 max are related. We have two equations that tell us that. And so when we measure VO2 max, we account for both heart rate and something called arteriovenous oxygen difference. Heart rate is measured, and we assume that arteriovenous oxygen difference are not different between visits. And then we saw no change in VO2 max. So that difference was non-existent. It was accounted for. Mathematically, that also means that cardiac output, or Q, was accounted for and was not different between visits. So stroke volume is our culprit, and stroke volume must not have been different between visits, even though we saw that decrease in stroke volume over time. And so unfortunately, our methodology that we use to measure stroke volume does not allow for measurement during maximal intensity exercise, but we were able to measure skin temperature during maximal intensity exercise, and through a series of assumptions that can kind of clue us into changes in VO2 max over time. So if we look at our skin temperature data, you can see here skin temperature has an inverse relationship with stroke volume. So when skin temperature rises, that indicates that stroke volume is decreasing, and that makes sense. During our work bouts, right, we see that increase in skin temperature during the same time that we saw that decrease in stroke volume. And something to pay attention to here is that during rest breaks, our skin temperature came all the way back down to baseline. And the key point here is that during our max test, right, when we measured VO2 max, skin temperature remained low, even though our workload was increasing again. We didn't see that increase in skin temperature. So what this probably tells us is that maximal stroke volume was able to be achieved during measurement of VO2 max, and that sort of helps us explain our results and why they're different from what we hypothesized. So in conclusion, we found that over two 45 to 15-minute work-to-rest cycles following those NIOSH guidelines, that cardiovascular drift did accumulate. However, VO2 max was not different between 15 and 120 minutes. And despite these rest breaks, cardiovascular and thermal strain were both amplified over time. I want to thank my participants. I want to thank Hillary, Brooke, and Allie for helping me with data collection. We did a lot of data collection. It took a long time, so I really appreciate their efforts. Also, thank you to Dr. Wingo, Dr. Richardson, and Dr. Nguyen for their help with the manuscript. And thank you to NIOSH and the Deep South ERC for funding this study.
Thank you so much, Anne. That was very, very interesting. Let me see here. I think one question was maybe this, just a clarification. How was body temperature measured?
So we measured body temperature wirelessly. We have these pills that the participants swallow 6 hours before they come into the lab. And then we have a little device. It kind of looks like a Game Boy. Anybody knows what a Game Boy is? And it wirelessly transmits gastrointestinal temperature from the pill inside the participant to our device, and then we can download that.
So that's basically the core temperature.
Yes.
So that's fantastic. Yeah. And follow up on that. So VO2 max was measured continuously?
VO2 max was not measured continuously. We measured VO2 max at 15 and 45 minutes of each work bout to make sure that our participants were working at the intended workload. And then for the last 8 minutes of the protocol. So once you saw that measurement of VO2 max, then VO2 max was measured continuously for the 8 to 10 minutes that it took the participants to run to exhaustion.
And that's wireless. How is it measured, just for my curiosity?
So we have something called a metabolic cart, and the participants wear a mouthpiece, and then ours has a nose plug, but you can get mouthpieces that cover the nose and mouth. They exhale through the mouthpiece down a tube. All of that air goes through our computer, and then it analyzes their oxygen consumption that way.
So it's not trivial. It's nothing like you can do. Just running in the park and you measure your view.
That's a backpack, so you could take it to the park with you, but that was not
okay. Yeah. Probably you cannot find many participants doing that. Let me see. Anybody else? Anybody among the presenters, if you have any questions? My field is definitely not kinesiology, but I think that has very good implication for occupational health and safety for exposure to heat of workers, because we always struggle to make them understand how exactly their occupation. I mean, the point is that their exposure is not. You don't really feel the heat exhaust right away. There is a lag time sometime, and then how do you explain them that this could happen for somebody who, even if it's fit or has perfect healthy, has this could have a heat stroke eventually. So you can demonstrate just showing the numbers, but you have to translate the numbers. Right. The manual you showed not the manual, the NIOSH booklet you showed, it's actually, I believe one of the main contributors is Dr. Bernand, who is part of this conference. So he's an expert in heat exposure.
Yeah, and those guidelines are great, and they're pretty extensive. And the biggest problem right now, the biggest unknown, is that while NIOSH has made all of these recommendations for work to rest ratios and percent work capacity that these workers should be using, there just isn't the data to support those recommendations. They haven't been tested yet. So that was sort of a secondary purpose of our study, was to just see if the specific NIOSH recommendations, so we followed their exact work to rest ratios, environmental conditions, workload. If you sort of followed their recommendations to a T, what would happen? So we sort of had a very picture perfect scenario, and we still saw cardiovascular and thermal strain over time. Right. So to take those recommendations and then put them in the workplace where people are maybe not quite following them to the letter. You might have people who are older, you might have people who have comorbidities. That could exponentially increase the problem.
That's a very good point. Indeed, I mean, those recommendations are mostly based on theoretical values which are obtained in the lab, and not much has been done to really expand this to practical measures in the field to collect really the data. So thank you so much. I think we're going to go to the next presenter, and our next presenter is Ivan Nair. He's a researcher at Auburn University in the Department of System Engineering. Ivan is going to talk about the validation of a wireless sensor system for the estimation of cumulative lumbar loads in occupational setting. And I'm glad to see you again, Ivan.
Thank you for your introduction, Dr. Lungu.
Sure. Please go ahead and present your work.
Okay, I'm ready. I cannot see my slides. Okay, so Dr. Lungo already mentioned the title of my presentation. Let me jump immediately to the introduction. Mechanical loading of the spine has been identified as an important risk factor for low back pain. Laboratory studies have investigated the effect of ergonomic interventions on spinal loading by estimating L5 S1 moments through inverse dynamic analysis, employing laboratory instrumentation such as optical motion capture systems, force plates, and boxes instrumented with force sensors. However, the effects of these interventions in constrained laboratory conditions might not reflect the effects of practice. In practice, therefore, it is recommended to perform these intervention studies in the real-world environment and the field. But it's hard for us to take our laboratories to the field. So an alternative to this is provided by inertial motion capture systems consisting of small inertial/magnetic measurement units, IMUs, measuring body segment orientations. So the goal of this study is to investigate if 3D L5S1 moments can be accurately assessed by using an ambulatory measurement system consisting of an inertial motion capture system. And the comparisons were made against a bottom-up and a top-down laboratory model consisting of optical motion capture system force plates. So regarding our instrumentation, the inertial motion capture system we use was the XSense system that consists of 17 Awinda sensors. And this system was compared against against 2 force plate and a 16 camera optical motion capture system, the gold standard that we're using, where we use 50 individual markers basing or the marker set in the plug-in gate, an adapted version of the plug-in gate marker set, where we added more markers, additional markers to have like better track of certain segments, especially the pelvis, due to the motion that we were requiring our subjects to do. And all the systems were synchronized using the optical motion capture system as the master system for triggering the signal. So we had 4 subjects from the university community. The exclusion criteria was no chronic low back pain during the previous 6 months, no diagnosed neurodegenerative disease, no injury or surgery in the low back region. And regarding data processing and filtering, the optical motion capture data was sampled at 120 hertz. The IMU data was sampled at 60. So the optical motion capture signals were downsamples to 60 hertz offline. Forces and kinematics were filtered using a Butterworth filter at 6 hertz for the optical motion capture data and 5 hertz for the IMU system. Biomechanical models employing both bottom-up and top-down approaches were used to analyze the data, and total moments were used for comparison. The total moments are the vector summation of the L5S1 moments on each plane, X, Y, and Z. And here you can see our task. Our task was basically, like our subjects were required to perform a task consisting of lifting and lowering a load of 10 pounds with no asymmetry to a height of 60 centimeters from the floor. Regarding the biomechanical modeling, the model we developed for the optical motion capture data was a 15-segment model. We developed it using Visual 3D. While the biomechanical model for the IMU system, we use the built-in model that is provided by XSense. The position estimate for the L5S1 joint was defined according to guidelines in the literature, using proportions of the anterior superior iliac spine, the ACES distance. The sternal load was assigned to both hands equally when the subjects were lifting and lowering the loads. And as a measure of system performance, we perform a repeated measures ANOVA. We compare the means and the absolute peaks of the estimated moments, and a significant level of 0.05 was used for all the tests. Additionally, we perform pairwise comparisons for the means and the peaks that we calculated, and root mean square error and absolute peak errors were calculated to compare the performance between systems. So, as you saw, like in the previous slide, the motion that the subjects completed can be divided in basically two main parts, the lifting part of the trial and the lowering. So on the top right, you can see the vector moments for the optical motion capture bottom up, the IMU top down, and the optical motion capture top down plots. I'm sorry, curves. And well, talking about the results, subjects were the main source of variability when we were analyzing the means and also the absolute peaks, while the models did not show significant differences regarding the models for the means and the absolute peaks either. The two key pairwise comparisons suggested that there are no significant differences between models, and we had the same results or similar results for the lowering task, where again, subjects were the main source of variability when analyzing the means and absolute peaks, while the models again did not show significant differences. The results of the two key pairwise comparisons, again, the same. It suggests the same, that there are no significant differences between models. And also, as I mentioned before, we compared the root mean square errors and the absolute peak errors between models. That means that in blue, what we have here in the different plots is the comparisons between the optical motion capture bottom up and the optical motion capture top down. In red, we have the optical motion capture bottom up model against the Xsens top down model. And in yellow, we have the Xsens top down model against the optical motion capture top down. So in summary, for the root mean square errors, the differences observed, like the values we obtained were around 15 to 25 Newton meters. And something very similar happened for the absolute peak errors for the lifting and the lowering. I forgot to say that, like, on the left side, we have the lifting, and on the right side, we have the lowering. So again, for the absolute peak errors, the results were between 15 to 25 Newton meters. So in terms of the discussion, well, like, what can we conclude? The estimates of the low back moments obtained from the inertial motion capture system are in close correspondence with the laboratory models, presenting no significant differences between model and concentrating the variability between subjects. The differences up to 15 to 25 Newton meters were observed between the absolute peaks and the root mean square errors calculated from the inertial motion capture system and the laboratory-based models. And those results are consistent with what we have found on the literature in this kind of analysis. And the approach taken to deal with external load application, assigning the load to the hands, could be promising to field studies in order to achieve ecological validity. So, as like the main takeaway for us regarding this pilot study is that we want to continue exploring the use of Xsens to finally use it on the field. There are some limitations for this study. The first one is, of course, the sample size. This pilot study with just 4 subjects. We need to explore, like, we would like to complete the same kind of analysis, but of course, having more subjects. The assumption of weight distribution on the hands. What we did is we assumed that the subjects were, we divided the load, the 10 pounds, assigning 5 pounds to each hand. And we know that in reality, that's not necessarily true. But for the top-down models that we developed, that was like the way we were testing here. The differences between segment estimations, for the optical motion capture data, we were relying on Bonney landmarks to measure the length of the segments, while for the IMU, the segment size is estimated based on the anthropometry data that you input, and also the segment orientation. So the segments are different, then we know that that's a source of variability that we want to explore further. Individual characteristics, of course, like we were testing in general, like young and fit people, same like with the past presentation, like obesity might be a factor, gender, BMI. Like there are things that we still need to consider for further analysis. And finally, another big limitation is the asymmetry. We're curious about what will be the effect of adding twisting to as a variable. It's not changing the slide. Can we go to the next slide? So yeah, this grant, the principal investigator for this grant is Dr. Sean Gallagher, and this is funded by NIOSH. So that will be the presentation. Thank you so much for your attention, and if you have any questions, comments, or feedback, they're welcome. I cannot
Thank
hear
you, Ivan. Thank you. That was interesting. Let me see. So one question, let me put it in a different way here. So if this the validity of this system is proved to be good, I mean to have similar characteristic with the system which you guys are using in the lab, does it mean that you can equip worker in the field and have them send out in the field and do their normal workload, and you can then monitor them afterwards and determine their spinal loading?
Yes, I mean our goal with this research, like the bigger grant that we're also developing right now, is to the future goal will be, yes, if the results are that Xsens is as good or similar to the gold standard or the silver standard, we would like to take it to the field, because this is an advantage of the system, is that it's not pretty bulky. So subjects in general workers will be able to complete their work and like the way they will normally do it. And for us, that's important because we want to measure the cumulative lumbar loads during their work routines, like as close to reality as possible.
So just to add to that, so this is designed to actually do more research rather than for workers to look at their lumbar spinal loading exposure, right? It's not used normally as an exposure tool rather than it's used as a research tool, right?
Yes, exactly. I mean, we would like at the end to get the cumulative lumbar loads, the results for those, like for that assessment. We would like to use it on the fatigue failure analysis to improve the tools developed at our.
Yeah, that's very important because you are basically looking at them in their normal working conditions. So we are not really simulating anything. It's their normal working condition, but you don't have to bring them in the lab and simulate those working conditions. So that's very important.
Yeah.
Let me see. I don't have any other questions here. If any of the participants have a question, feel free to ask now. We have another minute.
I have a quick question.
Please go ahead.
I'm doing a minor in industrial systems engineering. So this is what we do a lot, validating sensors against motion capture and force plate data. So I saw your RMSE values are satisfactory. Just out of curiosity, did you look at the R squared value?
Yes, we did. I'm having like echo. But yes, we did. We observed that the values were around 0.8 to 0.9. So
okay, great. I was just curious.
Yeah.
Thank you.
Yeah, I can share those results if you are interested.
I mean, that's important to share information so you guys can catch up later and share information. Thank you, Ivan. I'm going to introduce our next presenter. So our next presenter is Hilary Yoder. She's at the University of Alabama, and guess what? She's going to talk about heat stress, another of my favorite subjects. So the title of her presentation is Physiological Response to Heat Stress in the Groundskeeper. So you are in the department of, I don't remember. What department are you in? Sorry, you are muted.
Kinesiology.
Kinesiology, okay. Yeah, it seems to be a theme today. Okay, go ahead.
Okay. Well, thank you for the introduction. I'm Hillary, and like you said, I'll be reporting our results from our study on physiological responses to heat stress in groundskeepers. And I did this project along with Annie, who presented earlier, and a couple of my professors, Dr. Winchester, and my advisor, Dr. Wingo, here at the University of Alabama. Could I have the next slide, please? So why groundskeepers? Well, in the United States, there's nearly 1 million groundskeepers. It's an outdoor occupation, and especially in the South, they'll be exposed to extreme temperatures, including so like very hot temperatures like in the summer here. And this could increase their risk of heat illness. Along with the hot temperatures, they can be performing a variety of different tasks, such as planting flowers like you see in the picture, or they could be doing more intense tasks, such as laying sod or digging ditches. Next slide, please. So in these workers, we're hypothesizing that they're going to be exposed to heat stress and they'll be experiencing heat strain, which is a problem in these, which could be a problem with working outdoors. Another aspect we'll be looking at in these workers is their hydration. Maintaining optimal hydration is beneficial for worker health, safety, and physical performance. And lastly, we'll also be looking at their kidney function. Heat stress and recurrent dehydration may contribute to declines in kidney function. And just a reminder to everyone, our kidneys we have like two little bean-shaped organs, and they're about the size of our fist, and they're very important at rest. They receive about 25% of the blood that's being pumped out of our heart each minute. They're important for maintaining our fluid balance, producing urine, so excreting waste and filtering our blood. They help maintain our blood pressure, and they secrete hormones. So they have a lot of different roles in our body and are very important. So we're going to look at all of these factors in groundskeepers. We took 20 groundskeepers, which were 18 men, and we are anticipating having 10 more. We assessed them before and after work on 2 separate summer days. We looked at their resting blood pressure and heart rate, their core temperature, which we measured with the pill, the gastrointestinal pill they took at the beginning of the workday. We looked at their hydration status and habits, and we looked at their kidney function through a couple different biomarkers. What we found were a lot of our participants had hypertension, defined as a blood pressure of greater than 130/80 millimeters of mercury, so about 45% of our workers. Additionally, our workers on average were obese, so they had a body mass index of greater than 30, an average of 31. It was also very hot. The max wet bulb globe temperature during the workday, or WBGT, the temperature of what it feels like during work, was 102.4 degrees Fahrenheit. Their urine-specific gravity, a marker of hydration status, was 1.021, indicating they were dehydrated. It was greater than the cutoff of 1.020. And lastly, their estimated glomerular filtration rate, or EGFR, was less than 60 milliliters per minute per 1.73 meters squared in 6 of the 20 workers on both occasions, on both mornings for the workers. And just to give that a little bit of context, on Typically below 60 is considered diseased, and above 90 is considered normal kidney function. And for EGFR, we use the chronic kidney disease epidemiological formula, and in that formula, it considers age, gender, race, and it uses serum creatinine, which I'll talk about on the next slide. So before to after work, these are the means and standard deviations reported across both days, except for INGAL, which is only on day 2. So their urine-specific gravity didn't change pre to post work, so they didn't become more dehydrated across the workday. Their hydration status stayed the same. Their serum creatinine, which is a waste product that our kidneys filter out, did not increase pre to post work. And serum creatinine is a marker that's often used to measure kidney function. Although it's not perfect, it can increase for various reasons, such as if you do a really heavy workout, if you eat a lot of red meat, or if you take creatine supplementation, that can increase it as well. But we didn't see any increase across work for that variable. And then the last variable is urinary INGAL, which is neutrophil gelatinase associated lipocalin. And this is a protein, and it's upregulated during ischemic kidney injury, so reduced blood flow. We did see a significant increase in INGAL across the workday from about 2.8 to 4.5, although these are both kind of in a resting value range when there's some clinical values after people have had heart surgery or a kidney transplant, and those are around 50 to 100 nanograms per milliliter. So much higher than what we observed. Similarly, like after people run a marathon, INGAL will increase from, this lower resting range of the around 5 or so up to 35 or 40. So much larger increases are seen in different populations. Some more results during work. Their peak core temperature was 99.7 degrees Fahrenheit, which is considered to be mild hyperthermia. And that was their peak temperature, which indicates they weren't experiencing excessive heat strain during the workday. Their fluid intake was 2.3 liters per day, which, knowing that their urine was concentrated before and after work, it probably was not enough fluid. This 2.3 liters is about 70% water and 25% of sugar-sweetened beverages. The other 5% was coffee, milk, and milk beverages for the most part. So during work, they're drinking about half a liter of sugar-sweetened beverages, or SSB, and over a whole 24-hour period. So like the end of work the day before we saw them, and then until the end of work on the day we studied them, they were drinking nearly 1.5 liters of sugar-sweetened beverages in that 24-hour span. And to put that into a little bit of perspective, the US recommendations are to drink less than 1/4 of a liter per day, or less than 8 ounces. So in a 24-hour period, our workers were drinking nearly 6 times the daily recommended intake value of sugar-sweetened beverages. Okay, in conclusion, we observed low kidney function in our workers, but we also observed a lot of factors that could be contributing to this. First would be obesity. Obesity is a leading cause of kidney disease in the United States. Similarly, hypertension. A lot of our participants were hypertensive, and that is another leading cause of kidney disease in the United States. We saw that although 2.5 or 2.3 liters might seem like a lot of fluid to drink during work, it might not be enough for these workers who are exposed to hot temperatures, and they were drinking a lot of sugar-sweetened beverages. So their hydration practices, so the amount and what they're drinking, could be contributing to the low kidney function. And lastly, heat stress. It's got very hot during the workday, and that could also be contributing to their to the low kidney function we observed. And just some, limitations of our study is we didn't measure everything that could contribute to low kidney function. There could be other factors such as diabetes or genetic factors contributing to it. But overall, this study kind of shows that these workers might have, be at risk for developing chronic kidney disease. Some may already have it, but there's a lot of potential for interventions. For example, with hydration practices, it's really easy to, instead of having a 32-ounce sports drink, maybe have half of it and cut it with water. So you're still getting the fluid, but it has a little bit of flavor, and trying to increase water intake during the workday. Or with heat stress, you can do your more intense activities during cooler parts of the day to reduce your heat stress. And then diet and exercise can help modify your obesity and hypertension as well. And then I think on a last note, it's a lot of times when people have looked at chronic kidney disease and the development of it, they've looked at kind of the traditional factors such as obesity and hypertension, or they've looked at these kind of new factors of hydration and heat stress, but there isn't much known about how these interact. And so future directions could be looking at how these newer and more traditional risk factors for low kidney function are interacting with each other. And I'd like to thank our groundskeepers for their participation. They were very enthusiastic and made, waking up really early and to, do data collection much more enjoyable. And thank you for NIOSH for the funding for this study as well.
Thank you so much. Interesting. Actually, we did a study on exposure of groundskeeper to heat, and we didn't look at the physiological function, but rather what type of exposure they have a few years ago. So we have a few questions. Was the type of fluid the worker drank self-reported, or you guys control that in any way? So how was that done?
It was self-reported. So we gave them a fluid diary that since then I think has been validated. So they were given a diary that was like, kind of fill out your drink, what you've drank today.
So they choose whatever they wanted to drink.
Yeah, they just did whatever they wanted and just told us about it.
Okay. And there is a second question. So why did you use 130/80 for the hypertension, which is not exactly the criteria, which is currently used?
It is the criteria. The American Heart Association has updated their criteria recently to 130/80.
That's true. Yeah, that was the question. And I have a question. You are talking about kidney function, then they were low kidney function. Were these based only on the NGAL?
So more of the EGFR is the gold standard for measuring kidney function, although it's almost kind of like a fool's gold just because there's so many issues with it, but it's just really hard to measure kidney function.
Right. And as you mentioned, NGAL can be, you could see an increase in NGAL, but that could be for different reasons. So it's not necessarily, I mean, there is an increase even if you run outside for a mile. Yeah,
and I guess it's more of, we saw it increase. It increased a couple units, but is that really a meaningful increase? I think.
Any other questions from the participants? Nice work, guys. Thank you very much. I'm proud of you. I think that's, we're going to wrap up this session, and I think next is going to be the posters. The poster presenters we're going to choose the one which is going to, two awards actually, one for a master student and one for a PhD student who are presenting the posters. So thank you, everybody, and bye-bye.